Welcome to This Explainer. So, did you know that we've actually entered an era where machines are, well, literally programming themselves? I know, it sounds totally like science fiction, but it's happening right now, all around us. In fact, there's a really good chance that an underlying algorithm actually recommended this very explainer to you. Today, we're demystifying machine learning, taking you from those foundational concepts all the way to how it's actively shaping our day-to-day reality. Here is our roadmap for today. We're going to cover: what is machine learning? The 4 learning methods, the machine learning process, real-world applications, advantages and disadvantages, and finally, the top programming languages. And hey, I promise to guide you safely from the basic definitions all the way to massive corporate applications, entirely without getting us lost in the mathematical weeds. So, let's get right into it. Okay, let's dive into this. Section 1. What is machine learning? To really grasp machine learning, we kind of have to look at this massive paradigm shift in how computers actually operate. Notice how this brilliantly illustrates the difference. Historically, humans wrote a program, fed it into a computer along with some data, and the computer just gave us an output. Simple, right? But now we completely flip the script. In machine learning, we feed the data and the desired output into the computer, and the computer actually creates the program itself. Which leads us to this really profound quote, and honestly, the absolute core of our topic. If programming is automation, then machine learning is automating the process of automation. You see, writing software manually, it's become a massive bottleneck. We simply don't have enough human hours or developers to manually solve every problem on Earth. So instead, we're letting the data do the heavy lifting. Ultimately, machine learning is the only way to make programming truly infinitely scalable. To really ground this concept, think of machine learning like farming or growing a garden. The seeds you plant, those are your algorithms. The nutrients you feed those seeds to help them grow, that's your data. You are the gardener, curating the environment, and the plants that eventually sprout up are the programs themselves. It's so much less about sitting there writing complex math from scratch and entirely about nurturing algorithms with high-quality data so they can organically grow into highly functioning programs.
Moving right along to Section 2, the 4 learning methods.
Let's peel back the next layer of the onion here and explore exactly how these algorithms are taught. Looking at this fantastic, colorful mind map, you can see the sheer breadth of the field. I mean, you've got branches reaching out into everything from customer retention to robot navigation to game AI. It's a vast landscape for sure, but it essentially boils down to 4 main methods. Let's break them down sequentially.
First up is supervised learning. This is where algorithms are trained using explicitly labeled examples where the desired outcome is already known up front. It's basically like giving the computer an answer key. The learning algorithm receives input instructions along with the correct outcomes, then it compares its own predictions to those accurate answers and flags any errors to improve itself. This method is absolutely incredible for proactively predicting future events based on historical data. Think about it like anticipating if a credit card transaction is fraudulent before it's even fully processed.
Next up, we have unsupervised learning. Now here, the system is analyzing completely unlabeled data to identify hidden patterns and structures. In this scenario, the algorithm doesn't have that handy right answer up front. It has to figure out what it's looking at completely on its own. A perfect example of this is analyzing massive chunks of transactional data to cluster together customers with similar attributes for targeted marketing campaigns. The machine groups them based on hidden structural similarities that we humans might never have even noticed.
Then there's semi-supervised learning. Just like it sounds, this method uses a small set of labeled data alongside a massive volume of unlabeled data. The crucial takeaway here is that this method perfectly balances cost and efficiency. Acquiring perfectly labeled data requires a ton of human effort and money. For companies that simply cannot afford massive, fully labeled training sets, they just use a little bit of labeled data to point the algorithm in the right direction and then let it loose on the cheap, unlabeled data to figure out the rest. It's a brilliant compromise.
Finally, we have reinforcement learning. These are algorithms that use rapid trial and error methods to maximize rewards within a specified time frame. This heavily relies on an agent-environment dynamic, which is used a ton in robotics and gaming. The agent is the decision maker, taking actions within an environment. Every time it does something right, it gets a reward. Through millions of rapid-fire trial and error attempts, the agent learns to identify exactly which actions yield the absolute best rewards, eventually mastering incredibly complex goals entirely autonomously.
All right, Section 3, the machine learning process. Shifting away from the types of learning for a second, let's look at the actual step-by-step mechanics of how developers build these powerful models.
The core process fundamentally breaks down into 5 steps. First, you determine the specific problem you actually want to solve. Second, you hunt for and collect your training data. Third, you prepare and clean that data. Fourth, you train the model. And fifth, you test and validate it using separate test data. But keep this in mind, a successful architecture isn't just about the code. It requires solid human insight into both your business process and the overall quality of your data management.
Let's move to the next visual and see how this builds. Notice that iterative cycle here? Model validation is almost always a continuous, looping process. Improving the model constantly requires looping back around, tweaking the parameters, and gathering even more training data to refine its accuracy over time. It is literally never just a one-and-done process.
Let's move on to Section 4, Real-World Applications. Let's zoom out from the technical mechanics and look at our current reality, because the impacts across global industries are just staggering. In data security, algorithms can easily predict malware based on tiny 2 to 10% code variations. In financial trading, prestigious firms use proprietary systems to execute high-volume probability trades at speeds humans couldn't even fathom. Smart cars are using algorithms to adjust to drivers and road conditions in real time. But get this, in healthcare, machine learning algorithms reviewing early mammography scans have actually spotted 52% of breast cancers up to a full year before the women were officially diagnosed by doctors. I mean, that is truly life-saving technology.
Bringing it right down to recognizable corporate interfaces you might use every single day, take a look at these 2 examples. You see KLM Airlines utilizing a chatbot right within Facebook Messenger. Facebook has essentially turned Messenger into a giant testing lab for AI customer service. And then you have HubSpot's interface utilizing predictive lead scoring. They use natural language processing to identify really subtle changes in a company's structure to automatically pitch prospective clients. It creates incredibly smart, data-driven sales pipelines.
Section 5, Advantages and Disadvantages. Taking a step back for a balanced view here. Look, while machine learning is undeniably powerful, it's not magic, and it comes with very real risks. The pros are phenomenal. It easily identifies hidden trends, operates completely without human intervention, and continuously improves its own accuracy. But look at the cons. It requires massive, and I mean massive data acquisition, and super high computing resources. Most dangerously, it has high error susceptibility. If you train an algorithm with biased or incomplete data, you get highly inaccurate predictions. And because the system is autonomous, these blunders can set off a chain reaction of hidden errors that can go completely undetected for a long, long time, just compounding the damage before anyone even notices.
And finally, Section 6, Top Programming Languages.
Let's very briefly touch upon the actual tools data scientists are using today. Python stands out clearly at number 1. Its dominance really comes down to being incredibly adaptable, precise, and just an excellent general-purpose language for things like sentiment analysis. Right below it is R, which is a graphic-based language designed specifically for statistical computing. It's heavily utilized by data scientists uncovering hidden patterns at giants like Facebook and Google. You'll also see reliable mainstays like Java for big data management, MATLAB for numerical computing, along with Scala, C, and SQL rounding out the ultimate machine learning toolkit. So we've covered the what, the how, the why, and the tools behind machine learning. But as we wrap up this explainer, I want to leave you with a pretty provocative question to ponder. As machines continuously learn, adapt, and improve autonomously, what major human bottleneck will they automate next? The potential is truly endless, and we are just at the very beginning of watching this technology radically reshape our world. Thanks for joining me on this explainer, and as always, keep learning.